Hey there, chemists. In this lesson, we're going to look at how we use what are called Wittig reagents as a way of making alkenes from ketones and aldehydes. These are reagents that were developed by George Wittig, a German chemist who won the Nobel Prize back in the 1970s. And they're made from alkyl halides. So they look like this, these phosphorus-containing reagents, but they come from just halides. So I have an example of how we can take bromopropane and turn it into this phosphonium salt, and eventually this ylide. An ylide is a special word that means it's got positively charged groups directly attached to each other. This is a phosphonium ylide, and this is our Wittig reagent. So we often have to make them. So let's first show how we make them, and then we'll show how we use them. We can draw a mechanism right on top of this. They come from triphenylphosphine and something that acts as a base, like KOH. Triphenylphosphine, remember, has a lone pair on the phosphorus atom, and it attacks the carbon attached to the leaving group. The leaving group leaves. So this is just an SN2, which means we're pretty restricted in terms of good SN2 acceptors to make this phosphonium salt intermediate. Then to turn that salt into the ylide, we use the base. The base is taking away one of the two hydrogens that are on the carbon directly attached to the phosphorus. So draw an arrow from the base to one of those hydrogens. The CH bond breaks, and you simply have a pair of electrons and now a negative charge right on that carbon and phosphorus respectively next to each other. That's our Wittig reagent. So how do they react? They react with aldehydes and ketones to make alkenes. So here we have a ketone, but this also works on aldehydes. And it turns it into an alkene. Which means if you think about this, it's kind of like the opposite of ozonolysis. This is the reverse of ozone. Not in terms of how the reaction happens, but just in terms of a synthetic transformation. Ozonolysis takes alkenes and turns them into aldehydes and ketones. This does the opposite. So if we're planning a synthesis, we can think of those two transformations as kind of complementary pairs. So how this happens, let's redraw the ketone and show the Wittig reagent as an ylide. There's a plus on the phosphorus, and a minus on the carbon. Now in order to do this, we need to make a carbon-carbon bond. We've got a very electron-rich carbon on the Wittig reagent and a fairly electron-poor carbon on the ketone. So they will react with each other. You should have an arrow from that negatively charged carbon to the ketone carbon, and if you send that pi bond up, you get an intermediate that has a negative charge on the oxygen. And then you have this phosphonium, like so. This is another example of a neutral molecule that happens to have separations of charge. It's not like just some resonance contributor. This is the way to draw it. This has its own name as well. This is called a beta-ene. It's similar to the ylide up above, except in beta-enes, the charged groups are not directly attached to each other. And they're called this because similar types of beta-enes, however containing nitrogen, were first isolated from sugar beets. So that's the etymology of this. This doesn't hang around very long. It actually just rotates around that carbon-carbon bond. In fact, this is not even a transformation. We're just going to redraw it. It looks like that structure first because the positively charged phosphorus wants to be pointed away from this negatively charged oxygen. But once you have this, you can hopefully see how these two things will react with each other, and you get a four-membered ring. Might look a little strained, but remember phosphorus is a very large atom, so it can accommodate the ring strain of this size. This is called an oxaphosphatane. Lots of good organic names in this reaction. And we are one step away from the product. The last step involves an opening of this ring where the carbon-oxygen bond breaks to make a phosphorus-oxygen bond, phosphorus-carbon bond breaks to make a carbon-carbon bond, and that's how you get your alkene. The byproduct is simply triphenylphosphine oxide, which is the more inorganic thing. Even though there's phenyl groups, it's not the main thing we're looking for. Now, we can't tell in this example, but I'm going to make a note. The Wittig is Z selective. This particular example of an alkene is neither E nor Z. It's neither cis nor trans. But if we did make an alkene that had alkene geometry, we would selectively get the Z, the cis alkene, even though sterically that looks less stable. And there's a homework problem on the back that has you practice that. So let's use the Wittig with some synthesis examples. Here we want to make a 8-carbon diene from cyclohexene and bromomethane. So I got a 1-carbon piece and a 6-carbon piece, and I need to make an 8-carbon piece. That must mean I need 2 of those bromomethanes. So what can I do to an alkene, and how do I make alkenes? Well, we just learned you can make alkenes from Wittigs. So if I think about a retrosynthesis, this could come from 2 aldehydes at either end of a 6-carbon chain. Simply using a 1-carbon Wittig, I could turn this 6-carbon chain into my 8-carbon diene. And this dial could come from a cleavage of this cyclohexene. And each aldehyde could become an alkene with a 1-carbon Wittig that would come from our bromomethane. So we need to make the Wittig reagent. Let's do that first. To make the Wittig, you treat it with triphenylphosphine and a base. I'll just use KOH, easy enough to remember. That takes away one of the H's directly attached to where the bromine used to be, and now there's a phosphorus, or a triphenylphosphonium. Negative charge ends up on the carbon, positive charge on the phosphorus. That's your ylid. And then how do we use this? Well, cyclohexene we can do an ozonolysis on. Speaking of ozone being the reverse of the Wittig, we're going to use this right here. That will cleave the carbon-carbon double bond. Keep all your carbons, but now you have 2 aldehydes. And now we simply react this with our Wittig reagent, CH2, P, PH3, minus on the carbon, plus on the phosphorus, and you get your diene. You can imagine how much lengthier this particular synthesis would be if we relied exclusively on Orgo 1 chemistry, changing the functionality of the alkene, maybe to the aldehyde, but then having to do something like a Grignard addition to this to turn it into alcohols and then eliminations. It would definitely take at least an extra step or 2 to do the same transformation. Much faster to use the Wittig. Okay, so why don't you hit pause and see if you can attempt the remaining 2 syntheses, thinking back to knowing we're going to use a Wittig somehow. That means we have to have a bromide. In both B and C, we're not given bromides, we're given other oxygen-containing functionalities, and we have to turn them into these products. So hit pause and give those a try, and then come back. Okay, for B, I'm going to do a quick retrosynthesis for B as well. This is a diol, and there's only one good way to make a diol that we've seen, and that's from the alkene. You could do a dihydroxylation. And an alkene I'm going to propose we make with our new reaction, the Wittig. Now in this case, I could bring in a 3-carbon Wittig and a 6-carbon ketone, or vice versa. I could have a 6-carbon Wittig and a 3-carbon ketone, and both of them should work ideally. But I'm going to use the 6-carbon ketone and propose making it from a 3-carbon Wittig reagent, and you'll see why I think this one's a little better when we go through the forward steps. That Wittig reagent has to come from a bromide. And bromides can come from alcohols. We're using a lot of Orgo 1 chemistry in this. And alcohols can actually come from ketones, which is the other starting material that we have. So we got to turn this ketone into this alcohol, make the bromide, make the Wittig reagent, and react with it before we can hydroxylate it. So now let's go forward. Starting with this ketone, we want to turn this into isopropanol. You can do that with a reducing agent, LEH or sodium borohydride. And then to turn that into a secondary bromide, use PBr3. Now you're set up to do the Wittig reaction, or make the Wittig reagent, triphenylphosphine, followed by a base. We'll give you the ylid. Don't forget to draw the formal charges. They show not just charge, but actual numbers of atoms attached and electron count. And then we can react this with cyclohexanone. And we should get our alkene. But we're actually not done. We still want to dihydroxylate that to make our 1,2-diol. And if you think back to last semester, that's osmium tetroxide in the presence of some co-oxidant like peroxide. So rather steppy, but a good review of some Orgo 1 chemistry, reduction, bromination, and dihydroxylation. Lastly, we've got one more alkene to make. This time we only have one starting material. Luckily it's 3 carbons and we have a 6-carbon product, so we're going to have to do some manipulations of that propanol to turn it into things we need for this alkene. If we imagine making that alkene from a Wittig, it would come from acetone and the same type of Wittig we used up above, same type of ylid. And then to make these things, well, a Wittig reagent comes from a bromide. And in addition to making bromides from alcohols, don't forget you can also make bromides from alkenes, which we can actually make by dehydrating our starting alcohol. I have to make this ketone as well, so a little more retrosynthesis with this one. I'll just snake it down here. Ketones, you can make a couple different ways. One from Orgo 1 might be the oxidation of an alcohol, and that's useful for us because that can also be made from an alkene, which we can make from a less substituted alcohol. So, and notice we've actually already intercepted the same retrosynthon in this case. So both of these can go back to the same starting material. So we got to do a couple of different things with this starting alcohol to get the molecule that we want. Let's first show how to turn it into the ketone. So 1-propanol, we can convert to an alkene just with POCl3. We can treat that with oxymercuration, mercury 2 and water, followed by a reduction. And then we can turn that into the ketone with PCC. Alternatively, we could probably do a Wacker oxidation on this in theory and make the methyl ketone directly from the alkene. That would save us a step. Although, frankly, you can buy acetone, and as an organic chemist, you should know that. But we are challenging ourselves and saying this is our only starting material. Now, to take that same alcohol and turn it into the Wittig reagent, actually, we can start with the alkene that we just showed how to make. So now that we've shown how to make it, we can use it. Let's turn it into the Markovnikov bromide, just with HBr. Remember, peroxide would go non-Markovnikov, but no peroxide will go Markovnikov. And then we turn this into the Wittig reagent, identical to what we saw in the previous example, triphenylphosphine and KOH. Gives us the ylid. Don't forget those formal charges. And then we're set up to react this ylid with the acetone right above it. And that gets you to your alkene. So, there's a couple of ways that we can use the Wittig reaction in some synthesis, combining some Orgo 1 stuff, and Wittigs are made from bromides. Very useful reaction for making alkenes.